Hello there, Mr. Sutton here, bringing you this AP Calculus 2.1 lesson on intuitive limits of the finite variety. In this one, we are going to be finding finite limits using a graph. To open up our discussion of limits, consider the function below, f of x. So we've got x squared minus x over x minus 1. Pause the video and take a minute to just figure out what you think f of 1 should be. Alright, so if we plug 1 in for all the x values here, so 1 squared minus 1 and 1 minus 1, well, our numerator is going to come out to 0, and so is our denominator. So we end up with something like 0 over 0. Now, what is that actually? I mean, something divided by itself is 1, but when you divide 0 by something, you get 0, but when you divide by 0, you get undefined. So what should this be? I think we're going to call this does not exist for now. But that isn't really the end of the story. Just for fun, pause the video again and on your Desmos grapher, graph this out and see what's happening to the value of f of x, the y value, as your x value gets really close to 1. So here I am on my Desmos grapher. Let me do f of x equals, and actually let me reduce this so that we can see everything. There we go. Now I have a better look at everything. So let's do fraction. We got x squared minus x over x minus 1. So here is what that graph looks like. Now it looks like as our graph approaches 1 on the x value, we've got a y value that also looks like 1. Let's zoom in on what's going on there. And as we get closer and closer and closer, yeah, it definitely looks like 1 right there. But if you actually click on there, you'll see at 1 it is undefined. So if we go a little bit to the left of that, we see that as we're really close to 1 on the x value, we're also really close to 1 on the y value. And the same thing coming from the other side. And you could also make a little table for this. And if you create a number that's really close to 1, like 0.999, and 1.001, again, we're getting values that are very close to 1. So it's almost like there's just this little pothole in the road that would be 1 if we could get there, but we can't. So here's my table, a snippet from the table from before. There was kind of a close-up of the graph. And kind of our conclusion here is that the y value is approaching 1 as x gets closer to 1. So in that last example, we had the concept of what a function actually equals at a certain value and what it's approaching as we approach a certain x value. This gets us into the idea of a limit. So the basic idea behind a limit is the y value that a function is approaching as x approaches a certain value. So just to spell it out, when we write lim or limit as x approaches a of f of x equals L, here's what we're really saying with this fancy notation here. We're just saying as x gets really close to a, that's this x arrow a business, the y value, or f of x, gets really close to this y value of L. Just to apply it to the warm-up problem, we could say the limit as x approaches 1 of x squared minus x over x minus 1, we could say that that equals 1. Again, because as we get closer and closer to the x value 1, the y value gets closer and closer to 1. Note that the y value never actually equals 1 because our function is undefined at x equals 1, but it gets pretty close there. We're going to do a number of examples with graphs to kind of flesh out this difference between function values and limit values of a function, and we're going to start with these couple of graphs here. So pause the video, here's the first graph, and see if you can figure out f of 2 and limit as x approaches 2 of f of x for this first graph. Alright, so for f of 2, I'm just saying what's the y value on the graph when x equals 2. So at the x value 2, here is the y value up here. That appears to be 3. So that's what f of 2 equals in this one. Now for the limit as x approaches 2 of f of x, we're saying what is my function getting close to in terms of y values as I get closer to the x value 2. So if I come from the left or the right side, either way, as I get closer to the x value 2, I'm getting close to the y value 3 there as well. So it looks like f of 2 and the limit at 2 really are the same value for this first one. All right, pause the video and try out this next one. All right, so for f of 2, again, that's the actual y value of the graph at x equals 2. That's represented by this solid dot up here at 5. So that's our f of 2. The limit, on the other hand, at 2, again, as we approach from the left and the right, although the function ends up at 5, we're actually approaching the y value 3 right here from both sides. So our limit would actually be 3. So from this we see that although the function value and the limit can be the same number, they don't have to be. We could have a function value and a limit that are actually different. So we say that the limit and the function value f of a are sometimes equal, but not always. So for our next problem, we're going to take a look at this graph, and we're going to do so from the angle of something called a one-sided limit. What we've actually been using this whole time without even knowing it is a two-sided limit. With a one-sided limit, however, we're not looking at the place that we're approaching as we come from the left and the right. We're actually just looking at from one side what y value are we approaching. So for example, if I write the limit as x approaches a with a little negative up here, that's saying the limit as we approach whatever a is from the left side of a. So for example, if a is 2, you're saying, okay, as I approach from the left, so like 1.98, 1.99, what is my y value approaching? Now we can also do a right-sided version of this. We would call that the limit as x approaches a with a little plus up here. That's the right-sided limit of f of x, approaching the a from the right side. So for this problem, what I'm going to have you do is pause the video and see if you can figure out the left and the right-sided limits of f of x as we approach 2 right here. All right, let's see how that went for you. So as we approach 2 from the left side, limit from the left, that's coming from the left side here, and we see that we're approaching this y value of 3 at this open dot. Now as we do the right-sided limit, approaching from the right side, we're actually approaching a different y value. That's this y value up here of 4, this solid dot. The two-sided limit, just to officially define that, is going to be the limit as we approach whatever your x or your a is, whatever, from both sides. So as we approach from the left and the right. And this is what is usually meant when they say find the limit. They're talking about the two-sided limit. If the left and the right side limits are not the same, like in the example above here, then we would say that the limit does not exist. If the limits are the same, like we saw a few examples ago, then the limit is just going to be whatever the left and the right can agree on. We're going to go a little bit further down the rabbit hole now. Pause the video and try out the questions for this graph on the left here. So f of 2 and limit as x approaches 2 of f of x. So for f of 2, since there's an open dot at 2 and no solid dot to take its place, the function itself is undefined there. So we can write undefined, or in calculus we usually use DNE, that's does not exist. Next up, let's look at our limit. As we approach 2 from the left and from the right, we're approaching this y value here at 3. So there it is. And then let's try out this next graph on the right side. Pause the video and try out example 5 here. All right, so for example 5, f of 2, that's this solid dot up here. That's a y value of 4 up there. So that one does exist, and it's 4. Now for the limit, we actually have a different left and right-sided limit. From the left side, we're approaching 3. From the right side up here, we're approaching 4. So because we have these two different y values we're approaching, we're going to say the limit does not exist. If we can't agree on a single number, then there is no answer there. So just taking a look at some conclusions we can draw from these. If the limit of f of x as x approaches a exists, then what does that mean about f of a? Does it sometimes, always, never exist? Well, we see here, here is an example of the limit existing, but a did not exist, or the function value did not exist. And we've seen problems where the limit existed and the function value is the same number and did exist. So this is going to be a sometimes. If the limit exists, then the function value might, but doesn't have to exist. You could just have an open dot there. Now for this next one, if the function exists, then the limit sometimes, always, never exists. Well, which is it? Well, here on the right side, This is one where the function did exist at 2. We had this value up here, but the limit did not exist. And we have seen examples where we had some continuity going on where the function value and the limit were the same and both existed. So this is also going to be a sometimes. So in conclusion, just because the function or the limit exist, that doesn't tell you anything about the other one of those things existing. So at this point, we're going to pull together everything we've learned and give you another example here. So pause the video and see if you can find the following limits or explain why they don't exist. All right, so for a, this is the left side limit as we approach a here. We're approaching from the left side the y value 2. From the right side, for part b, the right-sided limit, we're also approaching 2 from that side. And now for the two-sided limit, remember, the left and the right limit have to match for the two-sided limit to exist. Since they both equal the same number, visually we're approaching the same value from both sides. That means that the limit is also going to be 2. The two-sided limit will be 2. And then finally, f of a, that's the function value there. Well, there's an open dot there, so that's a DNE, does not exist, or undefined. I'll just write DNE there for consistency's sake. Just for fun, we'll do one more example, different graph, a little bit more going on in this one. Pause the video and try these out. All right, so for the left side limit as we approach a, we're approaching this y value of 2 at the open dot here. And then for the right-sided limit, we're approaching the y value 3. Since the left side and the right side limits don't match up, that's what this is all saying here, that tells us that there is no two-sided limit. That limit does not exist. And then finally for f of a, that's the solid dot at a. That's going to be this 3 up here. So that's it for this one. I guess you've maybe reached your limit on Introduction to Limits here, finite graphing. Until next time, Mr. Sutton signing off.